Hey, hey, hey. Welcome to a world of laughter, learning, and entertainment. Welcome aboard as we set sail on a journey through liquid air. Liquid air is air that has been cooled to very low temperatures, cryogenic temperatures, so that it has condensed into a pale blue mobile liquid. It is stored in specialized containers, such as vacuum flasks, to insulate it from room temperature. Liquid air can absorb heat rapidly and revert to its gaseous state. It is often used for condensing other substances into liquid and solidifying them, and as an industrial source of nitrogen, oxygen, argon, and other inert gases through a process called air separation. In this section, we'll be shedding light on properties and its impact on our understanding of the subject. Liquid air has a density of approximately 870 km. The density of a given air sample varies depending on the composition of that sample, e.g. humidity and concentration. Since dry gaseous air contains approximately 78% nitrogen, 21% oxygen, and 1% argon, the density of liquid air at standard composition is calculated by the percentage of the components and their respective liquid densities. See liquid nitrogen and liquid oxygen. Although air contains trace amounts of carbon dioxide, about 0.03%, carbon dioxide solidifies from the gas phase without passing through the intermediate liquid phase, and hence will not be present in liquid air at pressures less than 5.1 atm. The boiling point of air is -194.35 C, intermediate between the boiling points of liquid nitrogen and liquid oxygen. However, it can be difficult to keep at a stable temperature as the liquid boils, since the nitrogen will boil off first, leaving the mixture oxygen-rich and changing the boiling point. This may also occur in some circumstances due to the liquid air condensing oxygen out of the atmosphere. Liquid air starts to freeze at approximately 60 K, precipitating nitrogen-rich solid but with appreciable amount of oxygen in solid solution. Unless the oxygen is previously accommodated in the solid solution, the eutectic freezes at 50 Kelvin. Welcome to the next segment, where we explore principle of production and its significance in our journey. The constituents of air were once known as permanent gases, as they could not be liquefied solely by compression at room temperature. A compression process will raise the temperature of the gas. This heat is removed by cooling to the ambient temperature in a heat exchanger, and then expanding by venting into a chamber. The expansion causes a lowering of the temperature, and by counterflow heat exchange of the expanded air, the pressurized air entering the expander is further cooled. With sufficient compression, flow, and heat removal, eventually droplets of liquid air will form, which may then be employed directly for low-temperature demonstrations. The main constituents of air were liquefied for the first time by Polish scientists Karol Olszewski and Zygmunt Wróblewski in 1883. Devices for the production of liquid air are simple enough to be fabricated by the experimenter using commonly available materials. Let's now turn our attention to process of manufacturing and examine its role within a larger context. The most common process for the preparation of liquid air is the two-column Hampson-Yulin cycle using the Joule-Thomson effect. Air is fed at high pressure into the lower column, in which it is separated into pure nitrogen and oxygen-rich liquid. The rich liquid and some of the nitrogen are fed as reflux into the upper column, which operates at low pressure 25 atm, where the final separation into pure nitrogen and oxygen occurs. A raw argon product can be removed from the middle of the upper column for further purification. Air can also be liquefied by Claude's process, which combines cooling by Joule-Thomson effect, isentropic expansion, and regenerative cooling. In this part of the video, we'll be diving deep into application and unraveling its profound impact. In manufacturing processes, the liquid air product is typically fractionated into its constituent gases in either liquid or gaseous form, as the oxygen is especially useful for fuel gas welding and cutting and for medical use, and the argon is useful as an oxygen excluding shielding gas in gas tungsten arc welding. Liquid nitrogen is useful in various low-temperature applications, being non-reactive at normal temperatures unlike oxygen, and boiling at 77 Kelvin. In the upcoming portion, we'll be dissecting transport and energy storage to gain a comprehensive understanding of its implications. Between 1899 and 1902, the automobile liquid air was produced and demonstrated by a joint American-English company, with the claim that they could construct a car that would run 100 miles on liquid air. On to October 2012, the Institution of Mechanical Engineers said liquid air could be used as a means of storing energy. This was based on a technology that was developed by Peter Dearman, a garage inventor in Hertfordshire, England, to power vehicles. I love interacting with my viewers, so leave me a comment and I'll do my best to respond.